Today we're going to learn about solution stoichiometry right here as you see it. This is just using stoichiometry to solve reaction questions that involve molarity. So we're still going to be doing stoichiometry just like before. We'll just be using molarity now because we have solutions. Here are some helpful hints. I'm not going to go over them. It's just things that you can use when you're solving problems. Look back at these notes. So here's our first problem. We're given a molarity, a volume, a molarity, two reactants, and we're asked about a volume. Oh my gosh, what to do? Well, first you need a reaction. So you have a choice whether you want to pause this and go ahead and figure out what the reaction is. You've been practicing that a lot, so it's always good practice. You could just copy down how I go through the solution. So you have to find what the reactants are, and then also figure out what the products are. Remember, we're just switching the places of the negative ions. So we have our two reactants, our two products. The next thing you're going to see is a balanced chemical reaction. And what you want to do with these problems always is to write down everything you know about a chemical above a chemical. So right here, 0.3 molar sodium hydroxide. I'm going to put that above the sodium hydroxide. You should write down 0.300 molar, but you're going to have to write two things here, so leave some space. I will put this 250 milliliters above the phosphoric acid, the H3PO4, and I'll put the 0.2 molar also above the H3PO4. So that's what it looks like. All right. So we've got all this information, and now you have to think about problem solving. Well, notice you have a volume and a molarity. Volume and molarity can give you moles. Sorry. So here's the process we're going to use. I don't know why the program keeps doing that, but we'll have to deal with it. So we have molarity in liters of the phosphoric acid. This can get us to moles. We'll use stoichiometry to get from moles of phosphoric acid to moles of sodium hydroxide. And then once we have moles of sodium hydroxide, we can get the volume. This is the unknown piece. Using volume is moles over molarity because we have the molarity of the NaOH. All right, so I'm going to solve it that way first. And I'll show you another way to solve this. So I start with my volume of the H3PO4 solution right here. I have to convert milliliters to liters because you can't use milliliters in these problems. Then I'm going to use molarity as a conversion factor, 0.2 moles per liter. So the liters cancel and I have 0.2 moles of the H3PO4. I have to use the volume and the molarity of the same chemical together. I cannot use this molarity for the NaOH with a volume of the H3PO4 because those are different chemicals. All right, so I did this step right here. I'm at moles of H3PO4. I can use the reaction coefficients, moles to moles, moles to moles, use the reaction coefficients here and here to get to moles of NaOH. I can solve that for moles of NaOH, and from my equation that molarity is moles over liter, I can solve that volume is moles over molarity. So here we go. Volume is moles over molarity. So I just found my moles right there. Divide by molarity of the same chemical. I have that right here. I don't even have to read the problem. Make sure you write the information about each reactant above that chemical so that you don't get confused by the words in the question itself. I don't have to look back here. Just look up here. I know I have 0.3 molar NaOH, so I put that in the denominator where the molarity is right there. And I get 0.5 liters of 0.3 molar NaOH. Now, one quick thing. I actually did set up these problems to be done calculatorless. It would be a good idea to just take some time to practice that. So this one is pretty straightforward. 3 times 0.2 is 0.6. 0.6 times 0.25, this is like 1/4. So 1/4 of 0.6 is 0.15. And hopefully you can see the 0.15 over 0.30 is a half. We could cancel out the 0.15 and the 0.3 and write 1/2 here, and 1/2 is 0.5. 3 sig figs because all of my items here had 3 sig figs, and there's no addition subtraction. Okay, the other way to solve this problem is doing a direct conversion, just doing this whole conversion all together instead of doing these 2 steps. I can use molarity as a conversion factor right here. So notice this is set up exactly the same way as the first one. It's just that now, once I'm at my moles of NaOH, I can use this 0.3 molar as 0.3 moles over 1 liter. I flip that, put the 0.3 moles at the bottom in order to cancel out the moles of NaOH, 1 liter on top, and then solve this. And again, you could do this without a calculator. You have a 3 here divided by 0.3 would give you 10 on top. So 10 times 0.2 is 2, and 2 times 0.25 is 0.500 liters. You get the same answer. Next problem. Okay, same idea. We're going to go through this thing. It's a different way of asking the question. There's a lot of different questions that could be asked in this problem. You don't always just follow this same method. You have to think about, what do I have and what am I trying to find? So this is why we put all of this information up here. Okay, you have to get your reaction, so it's up to you if you want to pause. I'm going to go through quickly how to get the reaction, but it's great practice. Oops. Here we go. We got our positive and negative ions in the reactants. Switch the negative ions to identify our products. Make everything add up to 0 and balance your atoms to get this reaction. Okay, now I'm going to put the information that was given from the question above each chemical in the reaction. So 50 mils, which does the 50 mils go with? 50 mils of this solution here. So I will put the 50 mils above the calcium chloride. I'll put the 20 mils and the 0.5 molar above the silver nitrate. And they've asked me, what is the concentration? You have to recognize concentration means molarity. You might want to write that down. Concentration is capital M. Capital M is read as molarity or molar. It's the same as concentration. So that's the question mark here. Now notice I actually added a whole nother row here, this liters right here. Since I have to always use liters in my conversions with molarity, because molarity is moles, this molarity, this capital M here, is moles over liters, I'm just going to rewrite all my mils as liters. You have to get very comfortable with converting between mils and liters. You just move the decimal 3 to the left when you're going from milliliters to liters. Okay, so I have my balanced reaction. Let's see, I've got milliliters and liters of, I have molarity and liters of my silver nitrate. So I know I'm going to start with my silver nitrate because I'm trying to find something over here. And I just always start with my liters. It's easier, you could start with molarity, but your ladder will look funny. So I start with my liters, 20 mils, or 0.2020 liters. And then I convert to moles using molarity. I can go moles to moles using the reaction coefficients. Now, some students will take this ladder and continue it on, and over here, they would continue the ladder, and in the denominator, just put this 50 mils down here in the denominator. There is no denominator here, but they wouldn't have this here. Let me show you this. They would stick in 1 over, and I can't do that real quick. Okay, they would make this whole ladder look like this. This step here is this step that's happening right here. Now, I did not solve it that way, so I'm going to delete that. So you can solve for your moles, and then you know molarity is moles over liters. So we take what we got in this calculation here, divide by our liters to get molarity. And again, some students will put that there and just go directly to the answer. So you can just do one straight ladder to get to this, or you can ignore what I'm doing. Or you can just do it the way that I showed you the first time. Okay, now for the most complicated problem. Limiting reactants with solutions. When you do a limiting reactant, you know you have a limiting reactant because you have information about two chemicals and you're asked about a product. In these other questions, we were only discussing the two reactants. We didn't ask anything about the products, just questions about the reactants in both this question and this question. Only reactants were asked about. Now, in this question, you're given the information about two reactants and you're asked about a product. And remember, if we're given information about two reactants and asked about a product, that means we have a limiting reactant problem. Those are the hard ones, but it's not actually that hard. When we do these problems, to make them easy, we're going to just work with the net ionic equation, just like you've been learning net ionic equations, and we learned about ICF charts. We're going to put those together in this last problem. So I have already written down, you don't need to take the time to write down the whole reaction. I did the reaction and the net ionic equation for you. You're going to need to put the information about each chemical directly above the chemicals. So this 100 mils and 0.1 molar sodium phosphate will go above the sodium phosphate. The 200 mils and the 0.3 molar calcium nitrate will go above the calcium nitrate. And I'm not sure if I did it. Oh, I just converted those directly to liters immediately. So that 100 mils right here, I just wrote as 0.100 liters because it is 0.1 liters. And that 200 mils right here, I just wrote that in liters. I simplified the process and skipped a step here. Okay, now I'm just going to work with the net ionic equation because the spectator ions, so my Na plus and my NO3 minus are going to be spectators. This stuff doesn't affect anything. It won't affect how much calcium phosphate is going to form. So I'm going to do my ICF chart. Remember my initial moles. In the ICF, we put our initial moles in the first row. And to get moles, it's molarity times liters gives you moles. So that's 0.0100. When you multiply these together, that's 0.0100. Just keeping sig figs here. And 0.2 times 0.3 is 0.06. Molarity times liters gives you moles. I'm multiplying these together to get my moles. Now my change row, I just do minus x or plus x, depending on whether I have a reactant or a product. And then I'm going to set 0.1 minus 2x equal to 0 and 0.06 minus 3x equal to 0. Solve each for x and find which one gives me a smaller x. Once I get to the smaller x, one reactant is gone and the reaction must stop. So I'm just solving for the smaller x, and then I know to use that smaller x when I solve for each of these final amounts. I'm going to plug this smaller value of x into this equation here and this equation here, and this one is just x. So again, you solve for x for each reactant, and you keep the smaller value of x and plug that back into your original equations. And that's what I've done here. We find that the phosphate is completely gone. Note that the sodium ions are not gone. Sodium is still around. It was a spectator. It did not react at all. But the phosphate ions, if I could highlight just those phosphate ions, they are gone, 0. The calcium ions now, there's some of those left. The calcium ions, I plug the smaller x into this equation, I solve for what is left, and I get 0.0450 moles of Ca2 plus left. On the calcium phosphate, I just have plus x. So I know what x is, I know how many moles of calcium phosphate I have, and now let's go back to what the question asked. Let's see. What mass of precipitate forms? Well, I know how many moles I made. I can very easily convert that into grams using molar mass. I have 0.050 moles. You were given the molar mass as 310 point. Let's put a little point in there. And I keep 3 sig figs, and I get this is my final mass of calcium phosphate made. We also want to know what are the concentration of all the ions at the end of the reaction. Oh my goodness. Including the spectator ions. So I've got to find the Na plus the Ca2 plus, and the NO3 minus. Now, I have moles, but I asked for concentrations, so that's moles over liters. This is a little tricky. You have to realize we added 100 mils. We're adding that. When I say it reacts with, I'm adding this 100 mils to 200 mils of something else. So my total volume is going to be 300 mils because I'm adding two solutions together. I'm putting these two things together. So the easiest thing to do first is the calcium. So we're going to do the, phosphate was 0. So phosphate is 0. The calcium, I did this wrong. Okay, I think I have fixed that properly. I had accidentally put the X value that I got as opposed to my moles of calcium ions that were left. So we have 0.0450 moles of calcium left, right here, the calcium ions that were left. And molarity is moles over liters, so I need to use my 0.045 moles of calcium that were left and divide it by my total of 0.3 liters, the 0.1 plus the 0.2, because I have 100 mils and 200 mils, which is 0.1 liters plus 0.2 liters, divided by my 0.3 liters, and I get 0.15 molar Ca2 plus left. Now I'm going to hope I did the other two correctly. Let's see, spectator ions. Okay, the sodium ion. This is confusing for a lot of students. We started with 0.1 molar of my sodium phosphate. So I have 0.1 molar sodium phosphate, 0.1 molar sodium phosphate. Notice I have 3 sodium ions in 1 unit. So 0.1 molar sodium phosphate is actually 0.3 molar sodium ion. That gets a little confusing for students. This is an important point. I can meet with you if you're having trouble, and I can give you some practice problems like this. All right, so I know my molarity of the sodium ions. I know I had 0.1 liters, and molarity times liters gives me moles. So I have my moles of my sodium ions, and moles divided by liters gives me my molarity. So that would be 0.1 molar sodium ion. And then the last one is the nitrate. So let's look. Our nitrate, we have calcium nitrate. We had 0.3 molar calcium nitrate, but I have 2 nitrates in 1 whole calcium nitrate, so I have to double the molarity because I have 2 nitrates for every one of these. So the nitrates get multiplied by that 2 to get 0.6 molar just nitrate. Molarity times the volume gives me my moles, and I have this written right here. I've got my liters, my volume right there. So 0.6 molar times 0.2 liters is 0.12 moles. And then I divide by my total volume to get the molarity in the big solution of my nitrate ions. Okay, so there was a lot to this last question, the limiting reactant questions, and I just want to show you what this would look like in a beaker. So remember we had our total of 300 milliliters of solution. So I had 2 beakers, I added them together to make this 300 total milliliters of solution. I'm going to have 1, 2, 3 different ions in this solution at this ratio of 0.15 to 0.10 to 0.40. And then I'll have this calcium phosphate solid sitting at the bottom. So here I've got these nitrates, NO3 minuses. Now remember those polyatomic ions, they are atoms bonded together with a charge. So there's a little negative charge here, and here's our nitrates. I have sodium ions at the lowest concentration, calcium ions at a little higher concentration. I should really show you another half of a calcium ion here, but I don't want to pretend that we have half ions. But the ratio would be another half mole of calcium ions in here with the ratios that I've given for the nitrates, the sodiums, and the calciums. And then we have the calcium phosphate sitting in the bottom. So all the phosphate ions that were originally in that first solution right here, all the phosphate ions from that first solution, those are all sitting at the bottom with some of the calcium ions that were in this solution right here. That had some of the calcium ions. So some of those calcium ions are down here, and then the rest of them, they were in excess and they're still floating around, and all of the spectator ions are still all floating around, not doing anything, just being spectators. All right, so some terminology. You're going to run into this vocabulary when you start doing some problems. Titrations. These are experiments where a solution of a known concentration, and that solution is called the titrant, is added to a known number of moles of another chemical until all the reactants are gone. These moles are going to be dissolved in a liquid that is put under the other solution, and you use what's called a burette to add the solution slowly, and when all the reactants are gone, that's indicated by a color change. A couple more terms. The equivalence point, that's the point in a titration when all the reactants are used up. The end point is where the color changes. You want these two to be the same moment in time, so you choose an indicator that will change color at the equivalence point, so that the end point is when this indicator changes color, and you pick an indicator that will change color at the equivalence point. And the indicator is the chemical that changes color at the end point of the titration, and that is it.